Okay, thanks a lot for the introduction. So this is my last talk. So this is something actually I have already talked about actually a few months ago in this department. So I hope that I'm not going to bore you by too much. This is joint work with two of my students, Cong Ma, Yuling Yan, my collaborator Yuejie Chi from Carnegie Mellon, and Jianqing Fan from Princeton. Okay, so the problem is the following. So I think many of you know what is matrix completion. So I have already mentioned this multiple times. So basically, imagine that you have an unknown low-rank matrix to recover, and you observe partial entries about it, and you want to make some estimation about all of the missing entries there. Okay, so and it has found a lot of applications from sensor network localization to recommendation systems, channel estimation, computer vision, a lot of them. If you are interested in them, I'm happy to talk about it, any of them offline with you. So now one of the most popular algorithms used in practice is perhaps convex relaxation. So basically, you try to minimize some empirical loss function, except that you're adding some extra nuclear norm penalization in order to encourage the low rank structure. So this is already something that's very, very well known and very, very widely used in practice. What I would like to talk about today is one step further from estimation. So in the estimation task, basically, if I give you this set of missing partial entries, and then you use some algorithm, returns some estimate about the missing entries. But sometimes if you want to do a more careful or more informative kind of decision making, maybe you want to know a lot more about that. For example, if I tell you like this guy is an entry that I like to fill in. Now I would like you to tell me how confident you are about the estimate you return to the users. And in particular, for example, I might want to ask you how likely this is going to be close to the ground truth, and also maybe how different it is from the ground truth. And probabilistically, and this might be modeled by saying that maybe if I have some noisy entries there, maybe I would like to really report some kind of distribution about any of the missing entries. So this is kind of like coming back to a statistical problem about how to report some confidence interval that is likely to cover each of the missing entry. And this turns out to be very important if you want to make informed decisions for a lot of the tasks that I just mentioned. Okay, like recommendation system, like computer vision. Usually you need to tell the users the uncertainty about the estimate you have. Okay. And the uncertainty can be caused by a lot of different things. For example, since we have noisy data, so there is a distribution in accordance with the noisy distribution. Maybe because we are actually sample only a small subsection, a small fraction of the entries of the matrix. So due to these incomplete measurements, we might also have some kind of uncertainty happening there. Maybe we'll have some adversarial noise. Maybe you have some other kinds of unexpected effect. But basically, this is a task about how to assess the uncertainty, how to quantify the uncertainty for the estimates that we have. And this is a problem actually posed a few years ago in the high-dimensional statistics workshop by I think mostly by Andrea Montanari, posed it as an open problem for the community. So we now know a lot about how to produce confidence intervals for like lasso or sparse recovery problem. Now the question is that how are you going to do it if you care about what you care about is matrix completion? This is significantly harder than those sparse recovery problems. So what are the challenges there? Okay, so imagine that I want to assess the uncertainty based on this convex estimator. Okay, now the first thing that you might encounter is actually this convex estimator is usually highly biased. And the reason it is biased is basically because you're adding some regularizer there. So it sort of like bias you towards some smaller norm, because the nuclear norm regularizer encourages something that has smaller norm. Okay, so you have some bias, so you might want to take care of the bias in a careful way. Next thing, actually, probably the most challenging part is that it's very difficult to track the distributions of the obtained estimate, actually. So if I just give you this guy, which is a solution to a very sophisticated, complicated convex program, how are you going to identify the distributions of this guy? So there is almost no distributional theory claiming what happens for this particular case. Now, in fact, even forget about a distributional theory. Actually, even if you only focus on the estimation part, the estimation error that we know about for this part actually are already highly suboptimal. Even if I ask you to characterize not the distribution for a single entry, but a reasonable bound for the L2 estimation error, even for that part, we know very, very little. Or maybe we know something that's very conservative. So, but if we have a very conservative estimation error bounds, if you just want to use it to build confidence intervals, even though you can still have some valid confidence intervals, it will usually mean that you will get something that's overly wide. And if you have a very, very wide confidence interval, it's not going to be very useful in practice, because we really want to tell as much as information as possible to the user. But if it's very wide, it's saying much less. Okay. So all of this pose a lot of challenges for this particular problem. So in this talk, I'm going to split the problem into two parts. First of all, I'm trying to find a way to improve upon the estimation part. At least we try to tell you something that's much better than what is known in prior literature. And after that, I'll tell you how are we going to reinforce this theory to get something better. So this is my plan today. I'm going to first show you how to improve upon our estimation guarantee in terms of the L2 error. Maybe not very precise, but we need to first get something much better than the prior art. And after that, I'm going to bootstrap it or reinforce it in order to make sure that we can actually do something very, very precise for every single entry, either missing or observed. Okay. And when I say precise, I mean I'm going to tell you the precise rates and also the precise preconstants. And hopefully all of these things can match the information theoretic limits. Okay. Okay, so I'm going to start with some stability analysis, which is basically about how to improve the estimation guarantees. Okay, so this is a problem. These are my notations. I have a low rank matrix M star, which is rank R. Okay, and I observe some partial entries there. So this is some standard notation for matrix completion. Omega is my sampling set. I have some noise. So I observe partial entries, and each of the observed entries is corrupted by some noise. In this talk, I'm mostly focusing on ID Gaussian noise. It can be significantly generalized. Okay, and the goal is to estimate the ground truths. So convex realization for this part, the most natural way to do convex realization is to look at this problem. So I minimize square loss with respect to all the observed entries, and then properly penalized by some nuclear norm regularizer. Okay, so this is one of the most common way of doing this. Now, I would like to say a little bit about what is known in prior literature about this very, very simple but powerful paradigm. Okay, so in order to say, in general, this is an NP-hard problem, but if we have some nice statistical models, things are not that difficult. Okay, so let me make the following extremely simple assumptions, and in order to make sure that I have something concrete to say. Okay, so first of all, let me assume that there is a random sampling model. Each entry is observed independently with probability p. Okay, p is my sampling rate. Okay, so I'll write it here. So p is my sampling rate, and n is the dimension of the matrix. And in order to make sure that this problem is tractable, at the very least, I need to make sure that P is larger than log n over n. Otherwise, you will have a disconnected graph, which means that you will never be able to estimate the matrix. Okay, so and then I have a constant rank matrix. The rank is order 1, independent of n. I assume that this is incoherent matrix. If you don't know what is incoherence matrix, basically means that the matrix entries are delocalized. So there's no single entry that is very spiky. So basically the energy are spread out across all of the entries. Okay, so this is a very simple model I have. And then I have ID sub Gaussian noise with variance sigma square and 0 mean. Okay. Okay, so this is what is known in prior literature. So in prior literature, I think this was first studied by Immanuel Candice and Yaniv Plan 10 years ago, and they have this estimation guarantee. So basically, if you look at the Frobenius norm error, and this is the bound that they have, sigma times n to the 1.5. Now we would like to understand whether this is the right thing to do or this is something terrible. Okay. So there is a minimax statistical lower bound that people have identified, which does not take into consideration any of the computational constraint, but suppose I'm allowed to do anything, this is a minimax lower bound that you have. Okay. So under my assumption that P is larger than log n over n, and you can compare them, and you can see that actually there seems to be a square root of n gap between the lower bound and the bound achievable by Candice results. Okay, so there seems to be a large gap there, and motivated by this large gap, Martin Wainwright's group proposed that let's try to modify the algorithm a bit by adding some extra constraint that try to control the size of each entry. And then they get the following bound. Okay, and the bound looks like this guy. So I'm basically, so if you compare it to the minimax limit, I mean this part that depends on n and p are the same. The only difference is that there is a max here, and then extra max operator happening here. And which basically says that if the size of the noise is much larger than the size of the corresponding entry, and then this is tight. Okay, so there is a region where this is tight. Otherwise, this result will say, okay, the error is like flat, so it does not go down if sigma goes to 0. So which says that even if I don't have noise, this bound does not give you exact recovery. Okay, this is a problematic part. Even if sigma is 0, which means there's no noise, this bound does not go to 0. So there's this range where we have suboptimal results. Okay, and then Kolchinsky and Zibekov, I mean, they have a different algorithm, which is more like a spectral algorithm for doing the same thing. But their algorithm also achieved roughly the same performance guarantee. The only difference between these two is that I believe that for Wainwright's results, is because the analysis is not tight, so this can be improved. But for Kolchinsky's result, I mean, because they are using spectral algorithm, this is a tight result, but this algorithm is not optimal. Okay, so this is my understanding about their algorithms. Okay, so all of them put together, we know that we have some good understanding if in the small SNR regime, but there is a lot of lack of understanding in this regime, which probably is the most important regime in practice. Okay, so but it turns out that the extremely simple algorithm proposed by Immanuel Candice actually, even though their theory does not seem to match minimax limits, but empirically seems to be doing extremely well. I mean, they have in their paper they have done some numerical simulation, basically based on the model that I mentioned, and then they compare it with some kind of oracle lower bound. And for all of the parameters they have tried, the L2 error is within a factor of almost 2 away from some oracle lower bound that they derive. And so it somehow says that practically this seems to be working extremely well. And put in another way, the theory proposed by Candy's paper seems to be too loose, which does not seem to match practice, which does not seem to explain the effectiveness of this algorithm in the best possible way. In fact, in their paper, they also mentioned that their analysis seems to lose a factor of square root of n compared to some oracle lower bounds. So basically, in this talk, we're trying to say that actually this square root of n factor can actually be removed. So in fact, the performance of this simple convex relaxation paradigm is almost optimal up to some constant. Okay, so this is what I'm trying to illustrate in this talk. Okay, so what are the challenges there? Okay, so the challenges, so if you know about this, a little bit about this convex relaxation literature, usually if we want to say something concrete, we start with the KKT condition. We say, okay, since this is a convex program, sometimes a constraint version, if you start with some first order optimality condition, like KKT condition, and then if you are able to find the dual certificate, and you can sort of guarantee that the solution is, the right thing. Okay. Now, in the noiseless case, this is not a difficult one because, first of all, in the noiseless case, if you are expecting exact recovery, and your primal solution has to be the ground truth. Okay. So if you are expecting exact recovery. Now, the only difficulty becomes how to find the reasonable dual certificates. And there's a guy, David Gross, who's a physicist who blazed the trail by developing an extremely smart procedure called Goffin scheme to take care of this part. So there is a very widely applicable scheme, dual construction scheme, that allows us to find the dual certificate that justifies the optimality of this algorithm, if there is no noise. But if there is noise, everything suddenly becomes so difficult. And the main reason is that if you don't have noise, we don't know the primal solution. It depends in a very complicated way in the noise. We don't know the primal solution. And if you don't know the primal solution, you cannot use it to use the Goffin scheme to build the dual certificate. So you don't know the primal, you don't know the dual. And if you don't know anything about that, how are you even going to start by saying that, this is the optimal solution? Okay, so this is just one page technical slide about the difficulty there. Okay, so in summary, the analysis technique based on dual certification seems to be very difficult, and it has bothered the community for maybe almost 10 years now. Now, in this talk, I'm going to follow a different route. I'm going to take a detour by looking at a completely different algorithmic paradigm, non-convex optimization, and then I'll try to come back to say, actually, this is something that can actually help us understand convex relaxation. Okay. So what is the non-convex paradigm? The non-convex paradigm is the following. So since we are doing low-rank recovery, and we already know that we are looking for a low-rank solution, so why don't we just start by representing the matrix variable by 2 low-rank factors? Okay, so I'm going to represent my matrix by a tall matrix times a fat matrix with the corresponding rank. So this sort of gives me, a low-rank representation of the problem. And then I can again solve the empirical risk minimization problem, except that now I'm replacing my matrix representation by the multiplication of 2 low-rank factors. Okay, so this is basically a standard way to start with this non-convex optimization. Sometimes I would like to add some regularizer here. Basically, the purpose is to promote to accelerate the algorithm. And so basically, you get the better smoothness parameter, get better strong convexity parameter. But this is a typical paradigm that used in practice. And this has attracted a lot of attention from the community. Actually, so maybe 1 decade ago, there are some, some heuristic works there, and then until Andrea Montanari, who basically pioneered this direction. Although at that moment, convex relaxation was so popular, so even Andrea didn't advertise the non-convex part that much. But it has seen some recent revival here, actually, because mostly because that non-convex optimization works. For this particular problem, was much faster than convex relaxation. Okay, so there are a lot of things happening in the recent years. I'm going to give you just one example about what we can do. There are a lot of different non-convex algorithms that can solve this problem. Just one, probably the simplest method for solving this. Okay, so what we are doing is that, first of all, you try to find some good initialization, maybe using spectral method, something like that. And then you run gradient descent. Okay, I think this cannot be simpler. So we run gradient descent, choose the proper step size until it converges. And we can guarantee that an algorithm as simple as gradient descent is already sufficient to give us a lot of great performance guarantees. Okay, so now let's look at the performance of this simple algorithm. Again, let's focus on the the random model I have with random sampling, ID Gaussian noise, and true matrix, which I assume to be of constant rank and incoherent. Okay, so it turns out that just this very simple gradient descent algorithm with respect to the non-convex function allows us to achieve minimax limits throughout all of the entire region. Okay, so this somehow allows us to close the gap. Even though when sigma is extremely go to 0, we have exact recovery. If it's large, you will always matches the minimax limit up to some constant. Okay. So this seems to be something that's very, very attractive in practice, because it seems that somewhat surprisingly, non-convex algorithm is easier to analyze the performance compared to convex algorithm. Okay, so this is a somewhat surprising message for us. All right. Okay, so now let me give you a roadmap. Convex relaxation has been the dominant paradigm to analyze about 10 years ago. A lot of people try to make progress towards understanding this paradigm. And except for Andrea Montanari's group, they focus on non-convex optimization at that moment. But recently, most of the people focus on the non-convex part for computational purposes. Now, since now we understand a lot more about non-convex optimization, now the question is whether we can return to convex relaxation and to see whether we can really say something useful for the other seemingly distinctive algorithmic paradigm. Okay, so I would like to make this connection in the next few minutes. Okay, so my starting point, it's a motivating experiment. This is not first observed by us. I think it has been observed a few years ago empirically by other people too. So if I'm going to run these two different algorithms, the convex relaxation one and the non-convex one, okay. Now I'm picking a regularizer in a very specific way. The reason I picked this is to make sure that it looks closer to nuclear norm for this one, because there is a formula saying that nuclear norm of Z is equal to can be written in this form. Okay, so this motivates us to use this regularizer in the non-convex formulation. Okay.
How do you choose R, the non-convex version?
Okay, there are two. Okay, so here I'm assuming R is known a priori, but in practice you can estimate it using spectral method, using a lot of algorithms for doing that. Okay, so basically you compute the eigen decomposition of the data matrix. You see there some at some point there's a gap, there's a spectral gap there, and you figure out the spectral gap and you pick that. Okay, so all right, okay, so. And also for this talk, for the purpose of this talk, actually this is as I'm going to illustrate, this is going to be a fake algorithm. So this is an algorithm that will never be run in practice. So now I can tell you that, okay, some genie already tell you what is the true rank there. Okay. All right, so I have these two paradigms, and then I run them some simulation, and then I compare. Okay, so this is what I'm doing. I'm plotting the L2 error as a function of the standard deviation of the noise. Okay, so this red line is my L2 estimation error for the convex relaxation paradigm. The blue line is my estimation error for the non-convex optimization paradigm. So you see that they basically match. Okay, so at least from this plot, you can't really see the difference. Okay, now I'm also going to plot the distance between these two solutions. Okay, I'm plotting the distance between convex and non-convex solution in this green line. So you sort of see that maybe even though this is not zero, this difference is several order of magnitude smaller than the estimation error. So this somehow says that the convex and non-convex solutions seem to match empirically in a very, very precise manner. Okay, so this is my key message. Empirically, they seem to be extremely close. And if they are really extremely close, and then since I know, so if they are really extremely close, since I already know the performance of non-convex optimization algorithm, I know this is minimax optimal, and then maybe I can just propagate it to convex algorithm and say, okay, maybe this is also optimal. Okay, so this is going to be the paradigm that I have. Okay, so this is the main result under the assumptions that I have with ID random sampling, random noise, rank is constant, well conditioned, incoherent, these kind of standard conditions. Now, if I look at this convex program, this is the theorem that we can say. Okay, so I have two messages. This is the convex relaxation algorithm. This is my message. First of all, the convex solution is almost rank R. Okay, even though I have not really used any of this rank information in this algorithm, but I can sort of guarantee that the solution is nearly rank R. So what this theorem is saying that if this is my solution, if I project it to a rank R space, I look at the difference, the approximation error, and it's much, much, much smaller than my estimation error. Okay. So this is the first message. It seems that convex relaxation, the solution is really nearly low rank. And if that is true, and then we can propagate what we know from the non-convex theory to convex, and eventually we conclude that the convex solution, it has an estimation error that matches the minimax lower bound. Okay, so eventually from this picture, basically this is what we are saying. We are able to show that even for simple convex relaxation paradigm, we achieve minimax performance. Okay, so just one more thing. In case you know what Martin Wainwright's algorithm is, they basically, except for this standard convex relaxation, they impose an extra condition which controls the spikiness of the solution. We want to control the this is entry-wise L infinity norm. So basically the maximum entries, size of the entries. If they impose this, they can say some nice theory if the sigma is very large. But what we are able to say using our theory is actually this part is probably you never need to enforce this guy, because your convex program automatically controls the spikiness of the solution, even if it is not explicitly implemented in the algorithm. This is something that we call implicit regularization. You don't need to add this regularizer, but the algorithm automatically biases you towards a solution that satisfies this. Okay. Okay, so this is, so far I have mostly talked about the case when rank is order 1. If rank becomes larger, you have something similar, but now our theory becomes suboptimal in terms of its dependency on the rank. So first of all, I need the sampling rate to be larger than this guy, which is already not optimal. So usually you don't need R squared. Information theoretically, R should be fine, but now I need an extra R factor. If that is true, and then I can still justify that, it is nearly low rank, and you have a performance that is minimus optimal. Okay. But again, the sample complexity bound is already suboptimal, and why this happened is because almost all the non-convex theory suffers from this suboptimality in terms of R, and this probably requires you to do something smarter in order to improve upon this. All right. Okay. So this is the estimation part. Now I'm coming back. I'm going to come back to say, okay. So now eventually my goal is to say how are we going to quantify the uncertainty, or how to build confidence intervals for all of the missing data. Okay. So this is the second part of the talk that I'm going to show you how to do it. So the way we do it is the following. Okay, first of all, I'm going to start with an estimator. This is usually what people do. I start with an estimator. Let's say the convex optimizer. And as I mentioned, this convex optimizer is biased because we have enforced nuclear norm penalization there. So we want to first remove the bias because we want to get the best possible confidence intervals there. So let's try to debias the estimate. And hopefully, after we do the proper debiasing, the distribution becomes some kind of approximate Gaussian distribution. If that is true, and if we are able to perfectly characterize what this distribution is, then maybe we can use it to perform uncertainty quantification. Okay, so this is going to be the paradigm. We're going to first debias it, and then we say, okay, how to derive a distributional theory for this. Okay, so how am I going to do the debiasing? So this is the first step that I have. Okay, so this is the first thing that comes into my mind. I have some random operator P omega. This is the projection onto the sampling set. You don't need to know what this is, but just one thing that I need you to know is that this parameter, on average, is identity. Okay, so treat it as an identity. So basically, you can remove it. And if you remove it, and then this is the rest that I have, and some of the terms cancel each other. So eventually, on average, the M star is the only remaining part. So somehow this says that if I do this, I'm going to arrive at an unbiased estimate of the ground truth matrix. Now, what is the issue there? The issue is that it becomes a very high rank solution. Okay, and why? Because I'm adding, this is low rank, but this looks like a noise. Okay, and if this is a random noise, usually it has a very high energy there. So this usually is high rank. So I'm starting with a low rank solution and adding a high rank factor. So eventually I get the high rank solution, which is usually not something that we want. And statistically, this is saying that somehow I'm boosting the variability of the solution by too much, even though this might be unbiased, but I'm significantly increasing the variance, which is not a good thing for us. Because eventually we want to have a confidence interval that is as short as possible. Okay, so now what I'm going to do is something very simple. Okay, so we know that this becomes a high rank solution. So why don't we just try to project it back to the low rank space? And this looks like, eventually this looks like one iteration of the so-called singular value projection algorithm. If you are familiar with the literature, but basically this is an extremely simple thing. I'm sort of like doing one step of gradient descent and then do the projection. Okay. And this is going to be my debiased estimator. Okay, so this is my debias estimator, and then so now I'm going to show that this really is almost unbiased, and after that I'm going to tell you what this distribution is, and then I can use it to build confidence intervals. Okay, so under the assumptions that we have. Okay, these are the typical assumptions that we already have. Let me just introduce one more notation. Okay, so this is my rank R estimator. It can be factorized in this way. Okay, and the ground truth can also be factorized by x star times y star. Okay, so these are just some standard notation. And I sort of like pick them. They are infinite way to do the factorization. So I'm going to pick them so that they are roughly balanced in the sense that if you look at x star times x star is equal to y star times transpose times y star. So just pick a particular way to remove some kind of ambiguity there. And if I do it this way, and this is my theorem, I can say that for either the x factor or the y factor, up to some global rotation, H is some global rotation matrix. After I properly rotate them, and the error looks like a Gaussian distribution. Okay, the error really looks like a Gaussian distribution. Okay, so and we know what this distribution is, and there are several messages there actually. So one thing is that this is Gaussian distribution, and every single row of this Z and Z matrix are independent. Basically, this is saying that your errors are going to decorrelate. So if you look at the error for the first row, the error for the second row, they are going to be nearly independent of each other. Okay, so and this is what we have for, if you look at a particular row, this is a distribution we have, and this is still not useful in practice because I do not really know y star and x star, but I can plug in my my estimator to get things right. So I plug in my solution, and then this is going to be roughly the distributional guarantee we have. So my low rank factors, if you look at the estimation error, it looks like a Gaussian distribution with the distribution that can be characterized using your estimator. And it turns out that this is asymptotically optimal in a very precise way. And on top of this, we are able to say that if you look at every single entry of M, if you look at the estimation error, it's going to be given by some Gaussian distribution with a variance that looks like this. It turns out that this is exactly the Quamara lower bound you have. Okay, so this is optimal, including the preconstant. And practically, you can basically just replace x star and y star by your estimator, and then you are done. Okay, so now we can sort of show that actually this is the distribution we have, and then you can use this Gaussian distribution to build confidence interval, right? You know that it is unbiased, it is a Gaussian distribution with no variance, and then you can use it to build any kind of confidence interval you want. Let's say 95% confidence interval, 90% confidence interval, everything is fine. So numerically, this seems to be doing quite well. I'm plotting the distribution of a missing entry with respect to the distribution of a standard Gaussian distribution. This is a QQ plot, so if you, which means that if it looks like a straight line, and it means that the two distribution match. Okay, so this seems to be something that looks reasonably tight. And the distribution of this guy really looks like something Gaussian. Okay, so as I also mentioned that the convex and non-convex solutions are roughly the same. So you might wonder, can I start with the non-convex optimizer and then perform all of the inferential results? Because they are almost the same, you can do basically the same kind of inferential procedure for either convex or non-convex. Everything will be the same. And the results are almost the same. So the same procedure simultaneously work for two completely different algorithmic paradigms. Okay. Okay, so maybe just let me give you a little bit of the intuition and then I'll conclude. Okay, so let me start from an extremely simple case when the ground truth matrix is rank 1. And let me start with the case when there's no missing data at all. So I observe every single entry of that. So this sort of becomes a matrix denoising problem rather than a matrix completion problem. Okay, now this is a non-convex algorithm that I have, and I'll try to show you how to analyze the distribution of why is it do you even hope this to be something that has some Gaussian distribution. Okay, so I'm looking at this one. Now how am I going to analyze the solution distribution of the solution to this non-convex program? What I'm going to do is to start with a first order optimality condition. Okay, so this is the gradient. I set the gradient to be 0. This can't be easier. Okay, so now let me look at this one. So if I look at this part, there's one part that results in some kind of bias, right? Because I mentioned that I'm adding some regularizer here, and which gives me some bias term here. So this is a bias that we don't like. But it turns out that this bias term can be incorporated into the other terms if we properly debias it. Okay, so the way that we do it is the following. I'm going to change x by xd, and this is a very, very simple calculation. You can do it in 10 minutes. But basically, you replace x by a proper scaling, and you plug them in, and you compare this with the original one. Basically, I'm removing the bias term. Yeah, okay. So this is basically what this debiasing procedure is doing. I'm trying to remove this extra factor due to the nuclear non-penalization, and then this becomes something that looks more like your original maximum likelihood estimate. Okay, so if I have this guy, and then after a little bit of manipulations, I just move some of the term to the right-hand side, and you can check that xd minus the ground truth is given by this term, which involves a noise term. E is a noise matrix. This is something related to the noise, and also something that looks like this. And it turns out that this term looks more like a second order term. If xd and x star is closed, this looks like a second order term. So you remove the second order term, and eventually you only have this Gaussian term. This something looks like Gaussian because it's a noise matrix times something that you have. So this looks like Gaussian. This is negligible. So, and this becomes the distribution or approximation we are going to use. Okay, so this is a little bit of intuition which can be significantly generalized. Okay, so finally, I'd like to just mention that if you are familiar with the lasso problem, for confidence interval for lasso, Chunhui Zhang and about 8 years ago, they proposed a way to do the biasing, very similar to this. Basically, it looks like something like this. So I start with the convex solution. I look at a linear map, some linear function of a gradient with respect to the least square part. We can also do something very similar as long as we choose this linear map to be this particular function, which is the projection onto the tangent space with respect to my solution. So T is a tangent space with respect to my rank R solution. And we can do this as well, and it turns out that they also match. Okay, so basically, you can find a lot of different ways to do debiasing, and all of them seem to coincide for the problem. Okay, so finally, let me come back to, this is probably one final message. Let me come back to estimation. So I have said a lot of things about confidence interval. Let me come back to estimation and tell you maybe one, somewhat surprising result there. Okay. So the distributional theory, why is it good? It allows us to understand every single entry, the performance of every single entry in a very precise way. Now I can come back to say something very, very precise. So now I come back to my estimator, my debiased estimator. This is not my convex estimator. This is a convex estimator after proper debiasing. And then we can show that even though the ground truth, I'm not imposing any distributional model there. But if you look at the L2 errors, it looks like this guy. It's 2 times n times r times sigma squared over p. With high probability, this concentrates around this guy. And this guy is precisely what Immanuel Candice showed as an oracle lower bound in their paper. So this somehow saying after proper debiasing, you're able to achieve Cramer lower bound in a very precise way, including the preconstant. Everything is true. So we get the precise characterization of the estimation accuracy. In the statistical language, this means that you achieve full statistical efficiency, including both the rate and the preconstant. And numerically, it does seem that after proper debiasing, this is the oracle lower bound. And this is the bound when you properly debias the convex estimator. It does seem that you get quite a bit of improvements there. Okay, so let me just conclude. The entire talk is trying to bridge convex and non-convex paradigms. And if you can do this, it turns out that we are able to establish near optimal stability guarantees for convex estimator. And also this allows us to demonstrate how to perform asymptotically optimal uncertainty quantification. There are a lot of questions. I don't know how to achieve optimal dependency in terms of the rank. I don't know how to deal with things when the true matrix is not well conditioned. What happens if the ground truth matrix is only approximately low rank? And how about you have more general sampling patterns rather than random sampling? Okay, so all of these we are going to leave it for future work. Okay, thank you very much.
Any questions for Professor Chen?
I just want to clarify. So when you try to say that this after debias is attended the CR low bound, so but you don't move back to the unbiased estimate.
Oh yeah, sure. For unbiased one, yes. Yeah.
So but this one is kind of the idea is that you say, okay, this is a biased estimate, and if you're doing this kind of unbiased technique, and they got the asymptotic optimal.
Yeah.
That's the logic.
That's the logic. Yeah. That's the rationale.
Lots of questions related. So now it seems like in the end of the algorithm, you have a post-processing step, but you can debias. So what can you output or utilize the debiased estimator in the algorithm at every iteration?
In every iteration.
It's like every iteration you.
An iteration of what? Of the.
For your gradient descent or something.
Okay, so for the non-convex one, actually, there's no bias there. Actually, if you just so I have a non-convex algorithm here. Okay, this is.
Intermediate procedure for solving a convex problem.
Then depends on how you solve it. So no, but before it converges, I do not really know how to debias it actually. Yeah, the theory only works when it already reaches the optimum of the convex program. So when you are operating in the middle, I do not really know how to debias in the proper way. It might be possible, but you will need more work. Now I'm not pretty sure that. And for the non-convex one, actually, I'm looking at this program. But usually, if you only care about non-convex, you are not going to add these things. These are stupid things to add. But if you just solve this, actually, this algorithm is automatically debiased. Actually, so there's.
You have good initialization.
I don't even think that's possible. I can't prove that, but I don't even think practically you never need to initialize it for this point, actually. Yeah, and it converges very, very fast. I don't think it's needed. Yeah.
So kind of a lot of related questions go back to the question. So in terms about the complexity interval.
Yeah.
So after debias, and even there's a CR upper bound, there are some unknown parameter like sigma square, the variance.
Our sigma square can be perfectly estimated for this case. It can be.
Do you want to use that result back to find the confidence intervals?
You can just plug this in. So you use another estimator and plug this in, and then it's fine. And so there's a multiple very easy way to estimate sigma. So you can, all of them guarantee that with high probability is accurate to 1 plus 1 over square root of n, something like that. So very accurate, and whenever you need that, you just plug them in, and then you are done.
So that will allow you to get the confidence interval.
Yeah, exactly. So my key point is that if you want to have confidence interval, the interval depends on a few parameters, and each of the parameter, we don't need a lot, at least a few of them, each of them can be estimated in a very precise way. So now you get, if you only care about 90% confidence interval, usually it suffices. Yeah. Unless you need, extremely accurate confidence interval.
Okay, so if not, then let us thank you.
Okay, thank you.